Hi, everybody. I'd like to talk today about this project which I wanted to build based on only biologically inspired methods without using traditional neural networks or anything like that. Let's speed this up. So there's a predator and prey relationship here, and they all start kind of at random. And over time, they actually learn. The prey learns to stay away from the predator while also chasing cheese. And if we actually really speed it up, and a little bit later maybe we can slow it down so as to see what the situation is. And as you can see, the mice are well, I call them mice, but they're supposedly trying to get to the cheese and while also trying to stay away from the predator. So this is accomplished by a continuous attractor network which detects food. This network is connected to three motor neurons. We also have boundary vector cells, which are a bit of like an instinctive reaction mechanism. They're not connected to the network. And also some hard coded instinctive rules, which we'll talk about. But this leads to learning, and the only connections that exist, which I will talk about a little bit more in detail a little bit later, are the connections between these 36 neurons in this continuous attractor network or the ring network. It's like a sensory apparatus to the motor neurons. And just from the simplicity, the amount of complex behavior that emerges is quite astounding to me. So there is obstacle avoidance, predator avoidance, and actually food seeking behavior. Although it's not the most sophisticated network, it actually works very well. By the way, the code files for this will be available at my Patreon. As a patron, you'll have access to the source code for this and 500 other projects, as well as my exclusive videos. Link will be, depending on where you're watching this from, in the comment and description. Here's another example of a single um, creature, let's say agent, actually learning to get to the cheese. Let's see what happens here. This is the same idea, but this time with a single agent. And it actually gets better and learns to kind of circulate around the food. That is due to the available actions, I believe. Should get better shortly. Let's talk about at an overarching level what these are. So this food direction network is kind of like a sensitive, kind of like a compass that is sensitive to the location, the direction of the food piece. And there's 36 neurons that represent the angle of the each 10%, 10-degree angles, and they light up in a population coding type of way. As you can see, like they light up as a gradient, decaying. Like the highest signal is at exactly where it's pointing, and then it has a fall off. And these are all connected to these motor neurons. The motor neurons are activated with a softmax. So essentially, if straight is like 70%, if the signals travel here, it's 70% goes straight, but 20% to right. Sometimes 20% will win. This actually makes for smoother movements. And the boundary detection, the boundary vector cells will actually detect the boundaries and the obstacles, and will produce an inhibitory vector that actually gets multiplied with the motor output vector. So it directly plays as an inhibitory role in the motor output. So this is a bit of like an instinctive mechanism. I actually had quite a long chat with ChatGPT about it. This is also biologically plausible. We'll talk about all the rest of the systems as well. Like I said, you can download the code files from my Patreon. The link for that will be below. And as a patron, you'll also have access to weekly meetings. So here's my first experiment without any obstacles, and you'll see that some interesting behavior evolved, such as spinning around the food for a while. This one actually didn't happen that way. This actually learned pretty efficiently, but let's run this again. Sometimes interesting behaviors emerge. out of this, like continually spinning around and like spiraling inwards towards the food piece. And you can see what's going on here more clearly since the ring network is larger. We'll run this for a little bit. The main learning here takes place from what's called the reward modulated Hebbian plasticity or Hebbian updates. Essentially, we keep track of which neurons have fired. This is normally in this type of learning, it's called like eligibility traces. But here in this case, it's a little bit easier than that because we actually make the updates at every step. Essentially, after a motor output is received, then we calculate if the agent got closer. Let's run this again. Actually, if the agent got closer to the food or not, and based on that, we know which neurons have contributed to it, and then we update those weights, strengthen the ones, reward the ones that have contributed to that action. This is also biologically plausible because in the brain, neural synapses that fire actually kind of tag themselves with chemical tagging, and when brain releases, for example, dopamine, then only the synapses that have tagged themselves actually receive that reward. As you can see, like it doesn't always learn, or it takes a long while for it to learn. Well, let's run this again. But so you can see that this is not a deterministic system. Oh, it started right where the food was. Let's see. So yeah. So as you can see, in this case, it was able to get to the food quickly. So it learns pretty quickly, depending on how quickly it gets to the food. Let's do this. Let's run this one last time to see if we can replicate the spinning behavior, because it's quite fun to watch. Yeah. Okay. I have one example at Twitter. Maybe I'll show you at X as an X post. Here is actually an example from my X post where the learning actually. Let's. I just rewinded it. You can see where the learning somehow the agent learned to just spin around. This is the same script we were looking at. So there's three different scripts with more complexity introduced at each one. The final one being the multi-agent. Yeah. So this, as you can see, we ran this like 5 times, and this behavior didn't emerge. So from these simple rules, very interesting behaviors can emerge. Interestingly. Another thing is that I should mention if you do download this code and run the prey relationship, it actually starts with a single prey, and you can add more by pressing space, and you just increase the speed. So this should actually result in some interesting behaviors too over the long run. Maybe um, I should modify this to see what interesting behavior would emerge. Anyway, coming back to this, this was because I have the explanation here. Maybe we can read from here. So each agent senses the world through a ring of direction neurons. By the way, if you like to follow me on X, my handle is at hive_echo. Each agent senses the world through a ring of direction neurons and a ring of boundary vector cells that fire when walls are near. Fast reflexes kick in immediately, bouncing off corners, peeling away from sudden frontal contact. This is a slower edge pressure builds if an agent clings to walls. There's actually a term here. Let me try to find. And it's something about it's called taxi something. It's about a rodent's wall hugging behavior. I'm actually currently asking ChatGPT about it. So the boundary vector cells also deal with that. The thing is, maybe it's here somewhere. Uh, that behavior is actually natural, so you can actually simulate. Oh yeah, thigmotaxis habituation, which decays over time. So actually, the rodents in real life do work like that. Apparently, like when they're introduced to a new environment, they do perform what's called thigmotaxy, which is kind of like wall hugging until they get used to the environment and they become more prone to traveling in the open space. So above these instinctive layers, it's a dopamine style reinforcement learner that is the reward modulated Hebbian plasticity, which uses eligibility traces that link recent actions to delayed outcomes, and a softmax action selector with the motor neurons that keeps behavior exploratory instead of deterministic. And so these are the biologically inspired features. The sensory rings encode target direction. These are continuous attractor networks. Boundary vector cells detect wall obstacles in 36 directions. The biological analog for this is antorhinol boundary vector cells, motor network with eligibility traces, learn turn policies from reward punishments. This is three-factor Hebbian learning with synaptic traces. So the three-factor is based on, let me explain this. So I hope I'm getting this right, but let's say there's a neuron and that fires, and then another one is the neuron after that. So when the first rule of this three factor is that when neurons fire together within a certain time frame, doesn't matter what, like maybe this one fires first and then this one fires second, doesn't matter, or this one fires and then this one fires, the connection between them gets strengthened. The second rule is the same thing, but this is A to B relationship. Let's say this is A. If A fires and right after that, within a short period of time, then B fires, then this connection actually gets tagged for potential improvement. But if B fires first and then after that A fires, that is not considered good. So this second rule is a sequential rule where versus the first one is agnostic to the sequence. If A fires, then B fires within a certain period, that this gets a tagging. And the third rule is that at the end, if after a certain time frame, let's say we take a look at the action that was produced, and if that action was good, then we come back and look at the eligibility traced connections, such as this one, and now we strengthen this one based on the reward value. So the reward in this case plays like a scalar. Okay, and we have the dopaminergic shaping, rewards for progress, punishments for setbacks, reward modulated plasticity, and hard reflex layer, instant wall avoidance, corner escape, brain stem, superior collicus reflex loops. I don't know if I'm saying this right. Edge pressure drive builds while wall hugging, decays in open space, stigmataxia habituation, and homeostatic motivation. So, if you're interested in these kind of algorithms, take a look at homeostatic systems as well. This sounds actually really interesting. Where I tried to implement it, but I haven't succeeded yet. Where we don't have many. This is not a great example of homeostatic behavior, but homeostatic behavior could be something like hunger, for example. Over time, the hunger increases, and when you reach food, hunger decreases, and you can modulate the weights of your network based on that. And softmax action selection and noisy competition, no arcmax like basal ganglia stochastic policy. So the softmax action actually happens with the motor neurons, so they are probabilistic rather than like just go left or right deterministically. This actually results in more smoother movements as well. So this was interesting for me. Let's actually play this again. See, live one last time. And I have some other experiments in the pipeline, so I should be making a video about them soon enough. Like I said, these projects take quite a lot of my time, and I always appreciate my patrons who support me so I can actually work on these experiments. So if you do enjoy them, please do consider becoming a patron. You will be able to download the source code for this project and 500 other projects that I worked on. I have quite a lot of LLM, large language model based projects. And I also make exclusive videos and I have weekly meetings with my patrons. And, you know, I think you might get some use out of it. I hope. And let's slow this down now and see. Oh, I forgot to add the additional prey, but actually single prey behavior maybe actually creates more interesting behaviors. So let's play it a little sped up. You can also see that the prey was caught 28 times, but was able to eat 220 pieces of food. Interesting. Yeah, I hope you enjoy this. There's quite a lot of interesting networks that you can use that kind of bring them together to build interesting things. Um, in any case, see you in the next video. Take care.